Hello, everyone. Welcome to another Wolfram Language Design Review, part of our series for version 14.1. And we have 3 design reviews coming up this afternoon. First one here is about PDEs. Okay. Where do I start?
You can start with the solid mechanics one. So there we have a new function, von Mises stress.
How many other stress functions do we have?
So there's the main stress function that computes the stress tensor from the strain. And
Okay.
this new function, the von Mises stress, takes the result from that stress tensor and simplifies it to a single.
Okay. Obviously, this is kind of illiterate here. I mean, there's no period. This is the wrong tense, etc., 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 right? Has this not been looked at by anybody?
Not yet. It's still futurized.
I understand that. But be great if you guys could get these things edited before I look at them, so I don't just feed you trivial edits.
Good.
I mean, yields the von Mises stress from stress. Okay, that doesn't make a lot of sense to me. And obviously, shouldn't be there. Yeah.
I think that this whole, the notes needs to be gone over a little bit.
And the example isn't right. So okay. So
yes.
Let me understand.
So the thing is that when we do, for solid mechanics in particular, we compute displacements. From that, we compute strain, from which we compute stress. But generally speaking, there are these quotes analysis functions.
I understand.
Okay, yeah. So this is one of those.
What other ones are there?
There are things we're making a catalog, and some of them are, brought up in these monographs, and they're living context in private contexts. But we would like them to be the things that you need to be system functions.
Okay, so hold on. I mean, we've had different approaches to this. Like with image measurements, we have a zoo of functions that are for all possible kinds of image measurements, and they're just all in one function with strings.
Yeah.
Right?
Yeah.
That's one approach, which I'm not that keen on. Because one reason I'm not so keen on that approach, well, it's complicated because, in statistics, for example, we have a bunch of functions which are just exposed, and it's like, its name. Well, like spatial statistics has a bunch of these where, its name, you care about that one, you just use that one. It's kind of convenient, but also, or like in, image processing, we have an awful lot of, beyond image measurements, we also have an awful lot of functions that are definitely minority use, like Chan-Vese binaries or something.
Yes.
It's kind of like really? I mean, is that, you either use it and that's what you should always use, or it has a, you see what I'm saying? I mean, in other words,
I think the von Mises stress is the most important stress measure that's in use. So I think that kind of warrants for its own function. If we then later have something like more exotic, we could package that up in a different way.
I mean, in other words, what is the von Mises stress really?
So basically, it gives you an indication of whether a material will yield or not. So if you deform an object and you get the stress tensor, then you usually have like 6 numbers, but you can't really say anything from that. So the von Mises stress takes those 6 numbers from the stress tensor and combines them in a sensible way into a single number. And if that number is lower than the yield stress of a material, then you are in good shape. Then you know that the material won't yield at that point.
So how does this relate to like principal components or some other such way of packaging up? I mean, you've got the stress tensor is what? It's a rank 2 symmetric tensor.
Yeah.
Is that right?
Yeah. Yeah.
Okay.
In most cases, yes. Yeah.
Okay. So what mathematically is this thing for a rank 2 symmetric tensor? Or is it nothing that anybody cares about elsewhere?
No, I mean this is based on von Mises failure criterion, and that's kind of I mean, the theory behind is quite complicated. So it takes the invariance of stresses and computes something sensible from them.
Well, I'm looking at the general formula, aren't I? Right there.
Yes, you are. Yeah, that's
right?
correct.
So for example, for the F mu nu electromagnetic tensor, what is this thing for that? I mean, that might be a physics question, but you understand? I mean, that's an.
I can't say that. I don't know. I'd need to think about that. I can't say anything about that.
So this is a thing mathematically defined on a tensor.
Yeah.
Except the way you're presenting it here with the U, V, W, et cetera, et cetera, et cetera. I mean,
so
it
the way
seems to be ignoring those things.
So the way it works is you give it the variables and the parameters in exactly the same way like you'd specify a solid mechanics PDE component. And you give it the stress tensor. That's the last argument you have.
Even though it doesn't actually depend on the function.
Correct. Because because it's just the same workflow for all functions.
Well, but if this was a well-known, the tensor hub or something,
yes.
If that was a well-known function of tensors, you would just apply that function of tensors, and von Mises would not be in the picture. Am I right? I mean, in other words,
I don't understand that.
Well, okay, let me give you an example.
Mm-hmm.
Okay, so let's say in finance, okay, there's the concept of volatility, but actually it's just variance, I guess, right? So given a time series there, we don't have to have a special function. Maybe we do because of crazy dates, calendar stuff, and so on. But in the first instance, it's just a mathematical operation on the time series, a well-known mathematical operation. So I'm asking, can this be thought of as a well-known mathematical operation on this tensor, as opposed to something which has sort of physics content that's, because look, there are plenty of
Probably yes, but the theory is going to be complicated for it.
Why? I mean, there's a formula right there. That's what you're evaluating, is that formula, right?
Right. But if you're arguing from that perspective, you might want to know, I mean, that there might be even more general approach to that.
Well, but there's this approach. I mean, in other words, if this was called the hub of a tensor or something, if this quantity was called the hub of a tensor, let's say, that's the thing.
Got it.
Then you would be happy to just say in your PDE setup, you would say, okay, let's compute the hub of the stress tensor. And I'm a little bit concerned here that this, that really this is an operation on on the symmetric tensor.
It's like a secondary step. You have to compute that tensor before.
No, I get it. I get it. But I mean, I mean, is it the case that there are PDEs in which you would have this function? I mean, in the PDE itself, does it have something that says that represents the stress tensor and then wraps this function around it?
You have that if you do plastic deformation, because then you need to know what the von Mises stress is at certain points in the object to decide whether it has plastically deformed or not.
No, but I understand, but that's post-processing. I'm asking, in the presentation of the PDEs, does this quantity appear?
No.
So this is pure post-processing?
Yes. The only thing that appears is stress.
The name is right. Yeah, I don't think the name is right, because I think you're making it look like, and the fact that you have completely redundant arguments here is not a good sign.
Okay.
But I mean, you get a scalar field instead of a matrix field out, right? So
exactly, yes. And does it matter what the Young's modulus and the Poisson ratio are?
No.
So this is just full of irrelevant information. I mean, really, this is a pure mathematical operation on a tensor.
Yes.
A tensor field, right?
Yeah, tensor field. Yeah. I mean, the question is whether we rather like to have a consistency in the arguments of all functions PDE modeling, or whether
but that's for the real time. that's for the equation components. All the stuff that you have there is necessary if this was appearing as something in the equation. But this is post-processing.
Okay, yeah.
Which is different from what you had elsewhere. You haven't had very many post-processing functions elsewhere, right?
Correct, yeah.
What happens with planar?
What do you mean?
No,
so if you, so plane strain and plane stress are different formulations of the PDE model, and you then use strain and the strain and the stress function to get the strain and stress out of them. There is no, that's not a post-processing thing.
Sorry. I got distracted by something. Could you say that again?
So what Roger referred to, plane strain and plane stress, are different ways to formulate solid mechanics PDEs. And they are not post-processing. So when you set up a PDE model, you can say you want this in a plane strain or plane stress form, but you then still do compute the strain and the stress as secondary quantities, and you're done with it. Then there's no function plane strain or plane stress or something like that.
Right. Yeah. But the thing I'm trying to understand is there any scenario in which inside the setup of the PDEs, there will be a thing that says, when event, this thing of something or other greater than whatever.
Yeah, for next release.
For plasticity, yeah, you can have that.
But is that something where this thing, would happily sit there in the PDE operating on a symbolic object? It wouldn't evaluate, and it only actually evaluates if it's given a specific and explicit tensor. To me, okay, this, the right name will be something like, von Mises stress, I don't know, measure criterion, I don't know, something like that.
Yeah.
So it isn't the stress itself. It's merely you give me a stress tensor and I'll tell you this measurement on it.
Correct. And that measurement typically is called the von Mises stress. So, but
I understand.
I see what you're saying. Yeah.
Right, but then the argument to that would just be a stress tensor as a symmetrized array, as a list of lists, whatever it is, right? I just don't know this field, so I don't know what else.
So for some, we need a little more information than that. For example, if the model form is axisymmetric, then the von Mises stress is computed a little differently. So we have to have this these parameters available to in some way.
Wait. Where are those?
So
my gosh, I don't know this field, so this is difficult.
Scroll down. The first. Let's see it in. The first is not a real example. You see there, when it computes von Mises stress, it's for a field.
Where the hell did it get the XYZ from? From the vase here?
Yeah.
Oh gosh. I don't think this is the right design, but I just don't know enough to be able to
Okay, then what is your concern basically?
That this is a post-processing thing, that it isn't
It is.
Okay, what other things are there that end with the word stress?
So this is the solid mechanics stress that computes the stress from the computed strain. You see that function in the example you just looked at. There you see the usage of it. So the first thing we compute is the displacement. Then we compute from the displacement, we compute the strains. From the strains, we compute the stresses. And from the stresses, we can compute the von Mises stress. So all of those in principle are post-processing steps, if you will.
All right. It at least has consistency. I'm not wild about it. I think there's probably.
Tell me what makes you worried. I'd like to know.
Well, because
My simple argument, Stephen, is that if these are standard things that you want to know, we shouldn't have them in a secret context.
Oh, God, no. No, absolutely not.
Mm-hmm.
Or you shouldn't have to program them yourself. That's another barrier.
Obviously. But I mean, the thing is, these things are things that appear in PDEs, right?
No.
This is a thing. What's that?
No.
Yeah.
Yes, and D-solve value of this equals, well, that's solid fiction. Oh, gosh.
The strain and stress are
post-processing. The solid mechanics strain and stress are encoded in solid mechanics PDE. So they are inside of that, basically. You need that to set that up, but you don't need the von Mises stress to set it up.
But that's only implicit, whereas here you're explicitly using it with this displacement as input to compute that. All right, okay, I'm sold. It's fine. Let's move on.
Okay. So for fluid mechanics, we don't have a new function. We've just generalized one material model, and we're making an application example. It's not quite ready yet, unfortunately, to show you. So,
but where is this new?
If you look at fluid flow PD component.
Oh, for God's sake. Arg.
You'll find there should be a version 14 plus tag on the Coro non-Newtonian fluid model.
It's right there, but there's no 14 plus.
It's a little further down there. Yeah. So it's just a generalization of the model that we've done.
What is mu?
I don't see the
mu.
Because of mu. So that's the apparent viscosity. That's defined a little bit above, like 2 items or 3 items above.
I thought eta was the usual symbol for viscosity.
Yeah, in this case, it's because it's apparent viscosity. For some reason, they've chosen.
But you've given the Reynolds number is the
so there is a difference between dynamic viscosity and
well, there is
kinematic viscosity.
Fluid. Yeah, for a non-Newtonian fluid, for sure.
Yeah.
I am not wild about using this curly thing for the Reynolds number. I mean, 99% of the time I see Reynolds number just written as RE, in ordinary letters.
But RE is a function, so it's a bit.
I know.
So I mean, if you, I'll change it if you want to.
I don't know. I'm not wild about it. I mean, I'm not.
Tell me what you'd be wild about.
No, it's not. It's okay. That's the kinematic viscosity, is that right? The mu there. That's the
dynamic viscosity.
What's the thing that's usually called eta? I mean, I usually see this formula.
Kinematic viscosity.
Okay. And but something is divided by density. One of them.
Yeah.
But there's a density right there.
Right. That's for the Reynolds number. Yeah.
No, I understand. But why?
So then you'd have the kinematic viscosity is then divided by, is the one that's divided by density.
Okay.
Check.
I mean, all of these endless names of people referring to things. I mean, it's kind of like I don't know how it works in these fields, but one of the things that has happened in physics is there used to be a thing, the Friedman universe model, okay, and then it became the Friedman-Robertson-Walker, and then the Friedman-Robertson-Walker-Lemaitre model, and over
family
time
names got longer and longer.
Yes. And because that person really had figured it out, and they had some lobbying organization, so to speak, that said you should mention them, blah blah blah. I don't know whether that's a risk in these cases as well.
Yeah. Okay, so kinematic viscosity is dynamic viscosity divided by density.
Indeed.
Yeah.
Right, but usually in the formula, there's I mean, sometimes I've seen nu as being the eta divided by rho, right? Look, there's probably a different notation for engineering and for physics.
Possibly.
And the question is, which one should we be using and how should we deal with that? Because like I'm reasonably aware of fluid mechanics, and I've never heard of this Caro, model. Okay, I haven't done stuff with non-Newtonian fluids particularly. But it's definitely not something I'm immediately familiar with, and it's presumably
So it's used to model blood flow and
yes,
plastic materials, as far as I know. No, yeah, and the model that we're working on is actually modeling blood flow.
How about ketchup?
Yeah, well, those are different. I mean, blood flow is specific. It has little things that align with the flow and they distort and so on. By the way, any word like, I assume you're reporting that as a spelling word and so on.
Yes. Yeah, absolutely.
Ali on our live stream comments, specialists in solid mechanics were more familiar with terms like mesostress. I didn't know there's some name that general
von Mises-stress.
Oh,
his
okay.
name is von Mises. Yeah,
I think so. Okay. What the heck is this? That is not something we do in documentation. What the hell is this? What is that?
So you can specify your own function for an apparent
okay, but that's not how we write it in documentation, is it?
How do we write it?
Oh, you know perfectly well. We do it with italics and we just say, function fun, and then you write fun there.
Okay, good.
What the hell is this blank, vase blank? Is that really what you write? I don't think that's really what you write. What do you actually write?
No, that's basically the signature of the function.
Okay, but that's not what you write. This is in a Roman font. That everything in a Roman font is what you actually type. You see what I'm saying?
I'll fix it.
Plain font is what you actually type. Anything, I mean, this is just wrong. I assume this should just be fun here. Right?
Yeah.
Viscosity, arrow, fun.
Yeah.
Right. Roger, how are we making sure that mistakes like this don't happen?
Look, I should have reviewed this. We should do a more careful review. So I'll make sure.
Okay. All right. Electric current PDE model.
Yeah, so that's a new function. There's a new monograph accompanying that set of functions.
I want you to see, do you have the decision diagram there?
Yeah, it's in the function page at the bottom.
Which function page?
So in the electric current PD component.
So
there at the bottom, it's a draft. That's
fine, but for Stephen's understanding, I think it's useful.
Yeah.
For people on the live stream too.
So if you scroll down to the function discussion, to the discussion part, you'll see scroll up a bit. Yeah, there. That's it.
Okay. So this is the sort of model world of electromagnetics.
Yep.
Different
for electrostatics to pure circuits to things with magnetostatics to
yeah, exactly. So the thing that we look at now is basically electric currents when the magnetic influence can be ignored.
The electric current is in the body of a material with skin depths and all that kind of thing, rather than just, there's this total current I going through this wire. Is that correct?
Yes.
Yeah.
I have to say, it would take me a little bit of thought to understand which aspects of, for skin depth, for example, in a alternating current and so on, don't you need?
Yeah. So basically, the function we're reviewing now is basically usable if the skin depth doesn't matter.
Okay.
then you can use that function. And that's the tricky part about electromagnetics, to dispatch on what function to use in what scenario. Because
you're right, but so I don't understand. I mean, in a conductor, why isn't the current just uniform across the conductor if you ignore magnetic effects? In a dielectric, I don't know what happens, but in a conductor, why isn't it just uniform?
Yeah, then you don't have so if there's no magnetic field, then there is no skin effect.
No, I understand.
So the skin depth is larger than the object size, and it doesn't matter then.
Yeah, but I'm trying to understand, why is there a non-trivial function involved if it's just there's a total electric current and you divide it by the area of the thing, and that gives you the current density. I don't understand why this is different from. I mean,
this is the PDE model. It's not the like the ODE.
I know, but I mean, isn't it uniform across the? Maybe I just don't know. I mean, okay, so for this conductor, presumably we're giving here.
So what we're looking at is
what the hell
basically
is that angle bracket doing?
That's the standard way how we describe that this is a PD component and it can set it equal to boundary conditions.
No, and that's how. What are the angle brackets doing in terms of our style for documentation? Is that something? What's that?
Yeah, we haven't really used that elsewhere.
And we really can't. I mean, we either have to introduce something as a big trumpet, thing. We can't just sort of start introducing it in random places. Not least because, we end up with automated systems that pick up things that we have in documentation and they just fail if it isn't consistent. Does that make sense?
Yep.
I mean, and similarly with this, which looks quite nice, is that something we've been using elsewhere? This kind of over.
We're starting to, because we haven't really explained much. Historically, our documentation really didn't explain that much, right? You assumed that you studied it elsewhere, and we were just giving you the interface.
I understand. I think it's good to explain stuff.
Right, and so we are doing that. So this, in some ways, this documentation is sort of leading.
Yeah. Okay. Well,
I realized something else, by the way, in our name. If you scroll up, so we call this electric current PDE component, but PDE stands for partial differential equation component, which is correct. But we should have coined a new term, PDC, partial differential component. We should have, it would have been much shorter. It's too late now, but we should have.
Yeah, it's okay.
So
what autocomplete
basically does, it takes the current continuity equation, inserts Ohm's law, and we use the fact that E is the negative gradient of the potential, and that's what we compute.
Okay.
And we do
electric
that.
Currents Monaco. Let me just look at this for a second.
Sure.
Oh, Christ. You can't do this kind of nonsense. No, don't do this. No, don't do it. It's a hack.
History. We've discussed this, Stephen. Everybody told you that's the correct way to do it. I don't know what else I should do. I mean, if
we should fix the system so you don't have to do this.
Please, yes, go ahead, absolutely. But until then, I have to do it.
You need to get this particular thing. Do I need to do it? Get it into the user assistance meeting. Get this discussed.
I'll do it again, no problem. But it's been there, and people told you no. They told you that's the way to do it. Mark told you, Itai told you.
I know. I don't think it's right. If we have to do this, we might as well just give up. This is just silly.
I'll bring it up again. Yep, no problem.
Okay, and the reason you're doing it is because you're building up. If you actually run all of this stuff, you're building up a lot of state, all these pictures and so on. Okay.
Yeah.
Just like this is so ugly. It's like okay, we're trying to explain something that's sort of a computational description of the world, and then we're thrust. I mean, by the way, I don't know why we need that either. Why do we need that?
Because we make use of low-level functions that are
okay,
not.
But they should be in the function repository. They shouldn't be in some random context
That's
like this.
Stephen. I've been working on this for more than 10 years. It's not an easy thing to just put everything simply in the function repository. We're talking about like 50,000 lines of code and more.
No, but that's not the point. The point is you have them in an internal context, but their exposure should be in the function repository if you don't want them in the system. Do you understand what I'm saying?
No.
Okay.
He means that the API call, you just call the same function, but you give another interface.
That same thing, right? It's the exact same thing, but there is documentation in the function repository.
I have documentation. Everything is documented. It's
where?
all there. It's all there.
Where?
You click on, I don't know, 2-element mesh and look at.
I'm clicking on this and it's not doing anything.
Well, yeah, okay. That's you just picked that single one that isn't there yet because it's a specific one for this example. Okay.
No, but wait a second. Look. We have a way of doing this now. We didn't have it 10 years ago. We do now. And the way is you put it in the function repository. It's a special purpose thing. It's used only in particular cases. Put it in the function repository. Okay, so that it has uniform documentation. So I, for example, know how to find the documentation, which I won't be able to do.
If you just click on it like 2-element mesh, there it is. Select it, press F1.
It's not the right way to do it. Where is that?
Yeah, there in the middle of the page, there it was somewhere. I don't know. Scroll up a bit again, please. We'll find one for you.
This thing here.
No,
I'm clicking on that and it's not doing anything.
Further up, one further up.
Wait. Is that a built-in function?
Just one thing at a time. One thing at a time, please.
Is that a built-in function?
No, it's not, but click on it and press F1. I'm
not finding anything. It's not doing a damn thing.
So it's going to the
there's no raft here. There's no where's the I raft here that gives information on this function.
On Windows, it's F1. On Mac, it's
I don't know. Maybe it's something. I mean, just
command. What is it? Command. How do you get?
How do you look up functions in the documentation, Stephen?
It's command something on Mac.
I'm using what this did. I pressed Command F1 and my screen went black, and it's still black.
It's not that.
What the heck just happened? Oh my gosh.
Does anyone have a Mac here and know how to select the function and look it up in the documentation?
Command Shift F, if I'm not wrong.
I did that.
There. So that's the reference page that goes with it.
It should be in the function repository. It should not be here. This is what we did years ago, and it's not what we should be doing now. We have a good mechanism for it now, and that's how we should do it.
Okay.
I mean, and this particular thing, so then we don't have a needs, we don't have any of that nonsense. I mean, that was the old world. We have, gone beyond that. What was I looking here? Was that? Oh, it was in the monograph, which I've now lost. Yeah, I mean, no. We've gone to a lot of trouble to get a system that's nice and,
Yep.
No. Put it in the function repository.
Okay.
I mean, yes, this was the right way to do it a decade ago, or the only way to do it a decade ago. Okay. Oh God. Sorry, it just annoys me to see all this stuff here. Although what this is doing is impressive.
Exactly.
That's good.
Why is that equation not magnified properly?
I filed a bug about that today. The equation setup is not looking good in 14.1 currently. Something is wrong there. Someone needs to look at it.
Okay.
So all this modeling.
This font, by the way, is wrong. I've reported this about 5 times. That font is wrong. Look at how big it is. It's just not right.
But generally, the page doesn't look right. I mean, there's very little space on the left-hand side, so something's wrong with the page generally.
Okay. All right. Okay.
Yeah.
These figures look kind of, like they were drawn in MacDraw.
Actually, this is a typical example. I was going to say that working on these modeling and applications where we use them really stresses and drives the framework forward. So in particular, the picture you have there, where you have like a cake of materials, you have discontinuities.
Yes.
And then you need discontinuities in your interpolating function, which in higher dimensions, which was something that needed to be worked out.
Is that a built-in function, line element?
It's a finite element context function. And this would be in the function repository then.
Yeah. How many functions are we talking about there?
I don't know. 50, 100. I don't know how many there are. 50 maybe, more 50, yeah. And tons of documentation. So I'm not even sure that the function repository is capable of representing all the documentation that I have, but I'll check that. Still there? Hello?
Yeah, I'm sorry. I'm distracted by something. Sorry. Well, it's lovely. I mean, the thing about something like this is, I mean, I'll really know if it's lovely or not the day I actually try to use it. And that will determine, I really can't tell. I mean, these pictures really look ugly. I mean, really ugly.
Yep.
Come on.
As I said, I filed a bug. I did file a bug about this.
Is that a problem with the rendering, or is that a problem with the picture?
I think in this case, the picture.
I mean, is this a TIM production, or is this
all pictures you see are programmed in Mathematica? So everything is done in Mathematica, in the language.
Okay, well, fine. But I mean, that's good. But it's just like somebody picked that blue, which is rather ugly.
So normally we have Tim go over these things, in which case they come out Timified, as we say.
Yes, that's what I would hope for.
Okay.
But that's not happening. That hasn't
not yet.
Okay, so that's just a yet, not a. Okay, fine. How far does the electromagnetics? I mean, like, if I want to design a weird fractal antenna, can I do it? Would that give me
probably not, because that's a high frequency thing, and we need full electromagnetic wave stuff, which we haven't done yet. So the next thing we're going to do is magnetostatics. We're almost done with that, but it's not going to make it for 14.1.
Okay.
But then after that, we'll do electromagnetic wave stuff.
Okay, cool. How many more domains are there that are kind of like common? I mean, that's a common one, obviously.
I think we've touched base with about all of them now. Now there's like cross coupling. Like, for example, if you want
chemistry would be one that uses a
chemical engineering.
Well, yes.
I mean, if you're designing a rocket,
we have mass transport, heat transfer. That's a lot of stuff.
Yeah, but you don't have phase change, like.
Yeah, we do. Absolutely. Okay.
Can you model a rocket engine?
I'm sorry?
Can you model a rocket engine that's full of phase change and so on?
I mean, I can't say. I haven't looked at that specifically, so I can't promise that it's going to work. But we can do model phase change, like melting of ice and stuff like that.
But like in system modeler, we have multi-phase flows and stuff. Do we have that here?
So what we can't do is free surface flow. if that's what you mean. That we can't do that yet. But that's still, I mean, Stephen asked about the fields that we've touched. So we've touched a lot. I mean, we've done something in fluid dynamics, but I mean, all of these fields can be fleshed out indefinitely.
And we haven't done general relativity, which I think is probably a field we should
that's
tackle.
Physics, Stephen. I need help with that. You know that.
Well, but I think we need to do it.
Yeah.
I mean, that's one that's important.
Yeah.
Oh, for what? For rocket engines?
No, for our users who are physicists, of which there are many.
I'm teasing. Yes.
So for the Schrödinger PD component, there's only a small change. The mass can now be completely anisotropic.
Why is that sensible? What does that even mean? When do you use that?
Yeah, that's beyond me. But
well, I don't think that makes any sense.
Michael discussed this, and they came to the conclusion it's useful, so we've done it. So there it is.
I don't know what the heck it's useful for. I have no idea.
So
maybe something in quantum
what
chemistry.
They've done this, they've used this in quantum dot computations of some sort.
I see. So it's an effective mass that is
correct.
Okay, all right.
But I'm a bit out of the depth here, so I can't really say much about that. So there's nothing else besides that single node that we've added. And there is the accompanying example, the axisymmetric quantum dot example is the example that goes with it.
These pictures are too big. I mean, they're actually not bad looking pictures, but they're obviously the wrong size here, right?
Okay.
Did you agree?
Yeah.
And also, look, we don't do figure 2. This is like this makes, this is like we're going back to, we have to print it on pages and we have to refer to figures because the figure might be 7 pages away type thing. This is very ponderously textbook written.
Okay, we'll remove those.
Well, I just don't think, no. I mean, this is not the style that we normally write these things in.
Stephen, I mean, that's absolutely fine. The problem I have is no one tells me stuff like this until I'm in a meeting with you. Why doesn't anybody tell me beforehand?
Well, because you guys are not interacting properly with, okay, never mind. But to be discussed elsewhere. Fair point. But, Roger can perhaps comment on this, but maybe not here.
Yeah.
Right.
Okay, so the last item on the agenda.
No, I want to see your quantum dot.
Okay, yep. Go ahead.
No dot has been seen yet.
It's just a dot.
I don't understand why these headings have lowercase letters here. That seems very odd. I didn't know that was our style.
Yeah, I've been instructed to only use lowercase letters in headings.
Width has a typo there. Come on, guys. Look at it. WIDHT? No. Where would that be caught?
Usually DQA gets stuff like this. But yeah.
Wait a minute. Where's the bottom line here? Whatever happened here? So I don't understand. What are we computing about this quantum dot?
So if you go down to the conclusion.
I did. The conclusion, it didn't have it. Oh, okay, it has it. What is this? I mean, this reads like an academic paper. That's not what this, I mean, what are we trying to do here? This is not the style we should be writing these in.
Okay.
It's just not the right thing.
Okay.
If it was an academic paper, fine. But, is it an academic paper? I don't think we should be doing academic papers. It's not our business.
Yeah.
That's for universities and places like that. They get paid to make academic papers. We do not. So what is this? What is the, I mean, I just don't understand.
So we use the azimuthal quantum number to compute these quantum dots.
Well, what do you mean by compute a quantum dot? What aspect of it? I mean, quantum dots
so we
are
set
being
up
used in quantum computers, for example. There's like, hello, it's a qubit type thing. And I don't know how much of that, is not pure one particle Schrodinger equation, but.
So we set up the Schrodinger equation for it and then compute the eigenvalues from that thing.
Okay, but look, the way people care about this is you have an array of these quantum dots and you're trying to make it into a quantum computer, for example. Right. So given that we can compute all this stuff about this quantum dot, what happens if we make an array of these things? You should be able to make a picture that shows, I don't know exactly what the right visualization is, but I mean, I just don't know what the conclusion is here. It just seems like it just sort of flaps around and doesn't, it looks lovely, but it's kind of like, it kind of needs a beginning, middle, end.
Yeah. Okay. We'll
Whereas
work
what
on
actually
that.
seems to happen here is the end is just like, oh, well, you could look at a different thing here. I just don't, I don't understand that this is not, like, what's the point here?
So the main point of this is to introduce the computation of quantum dots, and I admit I'm not an expert in this,
No,
so
I
I
understand,
can't really
but
I can't really answer your question now. So I don't
know
why
look,
this
it
is relevant.
needs,
But this is what
right,
Michael and Ricardo discussed and what they came up with, and
nobody
I trust
involved
that
in that is in this meeting. Is that right?
unfortunately
Because
not.
that's
No.
part of the rules for these meetings is, when you come here and you're like, well, I've got this thing and I don't know anything about it, it's not a very helpful meeting.
Yeah.
But I mean, look,
I agree with
I
that.
think with these examples, it's like normally in the examples you've shown for engineering type things, it's kind of like, and then the answer is the velocity field looks like this in a stirred, pot of this kind, right? So here, I just want to see the answer is.
Yep,
right?
we'll add that in.
Like, I mean, I don't know what,
place.
but just sort of going and saying academic things about it isn't really the point.
Yeah,
because what people are looking for is, I've got a problem, I'm going to use Wolfram language to get an answer. Not, this is a model for how I write a paper, which is their business, not, it's not really, that's not relevant. I mean, it's kind of like.
So we'll not have like this paper style.
No, I mean, I think what you need to do is say, we are computing, the wave function for a quantum dot in this situation.
Yeah.
And the answer is boom.
Okay.
Right?
Yeah.
And, maybe there's some extra pieces that say, and we could add this effect and that effect. And then when we add this effect, the answer is boom.
Yeah. Okay.
Right? Whereas what we're seeing here in sort of, I mean, presumably some of these things are answers.
Yeah, absolutely.
But I mean, it's not, I mean, is this the answer? We don't have a clue. I mean, this says boundary conditions in the eigenvalue problem solution. Okay. I mean, it's just not very clear on what the answer is. Whereas, the examples you've shown me before for PDEs really are very clear. This is the answer.
Right. Yeah.
Okay.
Okay.
Rather than I'm clever and I can say a few things about what's going on in the system. It's like,
correct.
Yeah.
I got it. I got it.
All right. I'm sorry. I'm just re-emphasizing because I'm clarifying.
I got it. Yeah.
And
it's okay. We'll change the style for those. Yeah.
Okay.
So
the next group here is it's primarily a set of examples, but the question is, when do you use ODE or lumped models versus when do you use a PDE and distributed models?
Yes.
And how can one use them together? Can you use, well, you can see the use cases there, from an ODE where you model typically a complex system, but then you want full details on something like, I think a room heating was here where you get the whole.
So then you're looking at the volumetric temperature in the room, even though you started off by just saying it's overall heated in this way. Is that right?
Yeah. So that's I mean, part of the how to say, challenge in this approach. So you have an ODE, a system model, but now you want to make a PDE model from it, or use the ODE model to drive the PDE model, but you need to make additional assumptions that are not present in the ODE model, because
Yes,
system model just doesn't care. So that's what's happening
and
here.
So how are you actually doing that?
So for this, so I mean, there is no final solution for that. In this case, what we've done is we've made it such that the temperature we assume with the radiator in the room is average. So on average, you have that temperature that the ODE model has. That's one approach to do it.
I see. But then you could, and then that's some kind of driving term.
Correct. Yeah. So you use the ODE, the system model result, to drive the PDE model. Correct. Right. But you need for this to work, and that's not a limitation in any way, but for this to work, you need to make additional assumptions for the PDE model.
For sure.
Yeah. So that needs to be done. Right.
Okay. I mean, seems interesting.
Yeah. And the other example is the other way around. If we can just briefly look at that, there we have a PDE model and derive stuff for a system model. So what we have here is
you're trying to get the aggregate spring, even though inside you're looking at the individual stresses and so on.
Correct.
And at the end,
But now stuff starts to get interesting, because we can do hyperelastic material models that are non-linear. So the spring constant is not a constant any longer, but we still can do it. So, and I mean, while it may be trivial to do for a constant spring, it's non-trivial for a hyperelastic.
I get it. So it's no longer a spring on a weight, where a weight on a spring, if the spring is hyperelastic, then it probably isn't a sine wave anymore, which is what you're showing.
Yeah, correct.
That's interesting.
And this is the more, I find the more interesting approach, where you have like a detailed drilled down PDE model.
Yeah, that's nice.
You do something that you can.
Okay, so what was the indicator that you used? How did you derive? So you've got the stress as a function of position. Well, in the end, it's the average strain or something that you want, which is the extension of the thing. Or somehow it's the average stress, average strain, or something. Or how does that work? Or is it some integral of those things?
So let me quickly look. So we have the displacement. So we have the displacement compared to the force, basically. So we know the input force to the deformation.
Okay.
So it's really straightforward. It's not as complicated.
Okay.
Yeah.
Very nice.
Good.
That's impressive. That's so. How many more? If you were, I mean, there should be one on quantum mechanics, presumably.
We haven't actually made these into books yet. There's still to do.
We're working on those. Yeah.
Cool.
But we're getting there.
All right. So look, some things about overall style that need to be aligned. But otherwise, very impressive stuff. It's I mean, it would be interesting to see at some point a multi-year roadmap for what, these different areas. I mean, we really should cover the physics areas. We have a lot of physics users. We really should.
True. But I need help with that. Yeah.
Well, fine. I mean, I would talk to Michael about it. I mean, that's and there are other people. I mean, Michael has some people who are definitely, physics enabled. I think it's just a question of switching around, who's doing what. But I would think, I mean, we need I think in physics we need optics type things. We need,
and that you mean not electromagnetic optics, or what you mean?
I guess it is electromagnetics. Yes, but I mean it's not.
Well, there are two ways. I mean, there's this sort of geometric ray tracing.
That's completely separate.
Ray tracing,
that's completely separate thing. That's not what we're talking about. I mean, for the physics stuff, it's mostly, diffraction type optics.
Yeah.
And then general relativity and quantum mechanics. I think those are the main things. I mean, yeah. All right. Well, sounds good. I mean, okay. And I mean, I suppose in solid mechanics, so it's not really physics, there's all the stuff with crack propagation and all these kinds of things.
Not quite yet, but we'll get there.
So the next thing is plastic.
Plastic deformation is what we're working on now.
Fair enough.
So if you deform something beyond the yield limit, it stays deformed because it's basically deformed.
And so that's kind of actually it's sort of interesting that if you had a regular PDE up until you reached a yield point, then you effectively change the PDE.
Right.
You know, when it's kind of like a fluid at that point, I guess.
Yeah, there's rheological models to do that. The problem is we have a working kind of a code, a prototype type of code that does what it's supposed to do, but the question is how to get that into ND-solve. So we're thinking about that. It's a bit tricky, but we'll figure something out that's hopefully reasonable and usable. So,
all right, good stuff. Okay.
Thank you.
I could see I really messed up my computer screens by that Command F1. I have no idea what it actually did, but they're all misconfigured now. Oh well, I have to untangle that. All right, thanks. Good stuff.
Yeah,
See ya.
thanks. Bye now.